we can project any vector onto any other vector. I mean, assuming they're both part of the same vector space. So, for example, suppose we want to project this vector onto this vector. It might seem like we can't do that because there's no way to construct a right triangle. But the projection will look like that. Because of this picture, sometimes rather than talking about projecting onto a vector, we might talk about projecting onto a space spanned by a vector. So let's say this vector is U. It might seem a little deceptive, or not deceptive exactly, but misleading to talk about projecting onto U when the actual projection misses U entirely. Therefore, we might talk about projecting onto the span of U. And now that problem goes away. The span of U is this entire line, and we really are projecting onto the span of U. And I mean, this is totally a terminology thing. Our formula isn't changing at all. We've still got our y hat equals this constant times U. So with that out of the way, let's do an example. Let's let y be 7, 6. And let's let U be 4, 2. And let's project y onto U. Now, as it happens, y is significantly longer than U here, but as we just said, that doesn't really matter. You're projecting onto the span of U. So here's our y hat, and there's our z. Y hat equals y dot U over U dot U times U. So let's see, y dot U, 7 times 4 is 28, plus 6 times 2 is 12, divided by 16 plus 4, all this times U. So that's 40/20 times u 2u 8/4. And then z is y minus y hat. So this minus this, -1, 2. And there's our projection.